Hello and welcome to the season finale, the final of the spring 2024 semester New York City Category Theory Seminar. Today we have Samuel Mimram from École Polytech, and he's going to talk about coherence and Cartesian theories using rewriting. Samuel, we have a little tradition around here. You tell us four pieces of information before you start: where you were born, where you got your bachelor's degree, where you have your PhD, if you have a PhD, and where you are now.
So I was born in Paris. I got my bachelor degree in Paris. I got my PhD in Paris, and I am now near Paris, I guess.
Perfect.
That's it.
Makes things a lot simpler. Okay, take it away.
So thank you very much for having me. I have 1 hour, right, or something like
Yeah,
this.
yeah, about an hour. You can go a little more, a little less, whatever.
Okay. So I will be talking today about trying to understand, might try to understand some issues related to coherence using Cartesian theories, so Liouville theory or term rewriting systems. So my goal is to have a better understanding of coherence theorem. So I mean, many people have a good understanding of this, I guess, but this was my own try, so I started thinking about this. And also maybe something which is a bit different from the standard tools, which is I want to try to have tools to show such theorems and generic tools or computational tools, if you so maybe so I guess all of you are familiar with let's say the basic example or the standard example of a coherent theorem, which is the one for monoidal categories. So a monoidal category, it consists of a category together with a bifunctor and a unit. And we have natural isomorphisms. So alpha, which correspond to associativity. So this is a natural invertible natural transformation. Lambda and rho, which are
Yeah,
also natural.
you can
Yeah,
go on.
yeah, natural transformation, which explain why, or which
Okay.
account from the fact that E is a unit. Okay, and you have two axioms to be satisfied. So this is MacLane's pentagon, and this is a triangle uh, axiom. Okay, so this is the definition of a monoidal category. And there is this very well-known coherence theorem for monoidal category, which is very useful because it avoids many computation in practice and simplifies everything, which says that every diagram commutes. So sometimes it says all diagram commute, so this is not entirely true, but what it says is that all diagrams whose morphisms are made of this associator and unitor does commute. So for instance, this diagram, so I didn't write the labels, but you can imagine that, for instance, this one here should be an associativity, so alpha. And so I don't have to try to think about how, but we know that it will commute using the previous actions. So in fact, there are various ways of formulating this coherence theorem. So you can think of at least three ways of formulating this. So the first one is what I call here coherence. So every diagram made of the structural morphism does commute. There is another one which we could call strictification, which says that every monoidal category is monoidally equivalent to a strict monoidal category. So it means that we can take all these structural morphisms to be identities. And it's not entirely obvious how the two relate exactly, even though they are quite closely related. You can expect that they are quite closely related. And there is a third way of formulating things, which I call here global strictification, which is somehow the second point, but taken globally. So what it says is that so you can build a two category of monoidal categories, and you can build a two category of strict monoidal categories. So monoidal categories where the structural morphisms are identities. And of course, there is a forgetful functor from strict monoidal categories to monoidal categories. So this is a two functor between two categories. And what you can show or expect to be able to show is that this two functor has a strict left adjoint. such that the component of the unit are equivalencies. Okay, so the component of the unit of the adjunction, J would correspond to this equivalence in point 2. So there are various variants, and as soon as you go to other structures than monoidal categories, then things start to be a bit less obvious to state. So for instance, the next thing to try is to have a look at symmetric monoidal categories. So monoidal category is symmetric when it is equipped with a natural transformation like this, which says that the tensor is symmetric. So x tensor y goes to y tensor x. And it has to satisfy some axioms, which I did not write here. And an important point is that we don't have anymore the fact that all diagram commute. For instance, here you don't expect that this diagram commutes. So here you have x tensor x, and the morphism above intuitively exchanges the two copies or swaps the two copies of x, whereas at the bottom you have the identity. Okay? So for instance, you expect that set equipped with Cartesian product should be a symmetric monoidal category, and you can easily convince yourself that this diagram will not commute. So the way we formulate coherence property in this way is a bit more subtle. So the coherence property, it says now that every generic diagram in a monoidal category does commute, where all the morphisms are structural morphisms, so made of alpha, lambda, rho, and now gamma. So by generic, we mean that, so when we try to understand or to give a reason why this would not commute, here we see that there is x twice, okay? And so we say maybe this is because of this, and so we should remove this possibility. So we want diagrams where all the variables are different, if you want. So here the x is somehow formal, and we don't want a situation where we have twice the same diagram. Another way to, so you also want to have a strictification theorem. So every monoidal category, symmetric monoidal category, should be symmetric monoidally equivalent to a strict symmetric monoidal category. So there is a symmetric missing here. And the important point here is that when we consider a strict monoidal category, we don't make all those morphisms identities, but only alpha, lambda, and rho. You don't want gamma to become an identity. And there is an analogous of the global strictification property. So there are very general theorem for this. So one is due to power, and I want to mention this here. So there is a monad T on cat, on categories, whose strict algebras are strict monoidal categories, and pseudo algebras are a variant of the definition of monoidal categories I gave earlier, which are unbiased monoidal categories. Okay. So if you want a monoidal category, you have a binary tensor, which is the tensor, and a nullary tensor, which is a unit. And in an unbiased monoidal category, you should also have all n-ary tensors. And this theorem states that the canonical two-functor from strict algebras to pseudo-algebras, so this forgetful functor, it admits a left to adjoint such that the component of the unit of the adjunction are equivalents of type pseudo-algebra. So in particular, if you instantiate, so it works for very generic, in very generic situations. So you have to have conditions on the monad T, but it works in quite a large generality. And for instance, for this particular monad T, it says that here you have strict monoidal categories, here you have unbiased monoidal categories, and you have this particular adjunction.
Okay, could you just say again what unbiased means?
So unbiased, it is a variant of monoidal categories where you want to have n-ary tensors. So you can tensor 5 objects at once and 7 objects at once and so on.
Yeah,
and
okay.
You want to have suitable coherence axioms for that. But of course, so in the bias setting, you only have 2 and 1 if you want. And of course, if you can tensor 2 and 1, you can tensor any number, but you don't have any direct access to this operation of tensoring n at once.
Okay,
So
thank you.
Here we want to investigate general coherence to theorems, which so the particularity of this work. So we want to address the case of biased notion of categories, okay, of monoidal categories, if you want, because this is what we use in everyday life. Also, we want to have partial coherence theorem, so in the sense of symmetric monoidal categories. So here we, for instance, we want to identify this part of the structure to identities, but not gamma. So this is partial, we don't quotient everything. And also, so this can be handled in other settings. So I don't want to explain this today. But also, one thing which some of the previous settings I have in mind could not handle is settings where structures where you can duplicate or erase variables. So if you want, for instance, to categorize the notion of ring, then maybe you want to have what is called a rig category, where you have two tensor products and a distributivity law. And the interesting point here is that here you have x twice on the right. Okay, so you want to be able to have this kind of axioms. Okay, and this motivates really the use of term rewriting systems or rewriting systems. Okay, but before I do concrete things, I want to try to understand the situation in a very general setting, in a very abstract setting. Okay, so this is what I'm going to try to explain to you first. So you should, so by an abstract setting, I mean that the structure is not really present, but still the situation addresses the situation, the more specific situation we expect to have in settings such as monoidal categories. And also, actually, we will see that we can use this somehow contentless approach in order to address the real problems afterward. So this is not only a purely theoretical way of addressing things. So we fix a category C, which we think of describing an algebraic structure. Okay. So for instance, if we think of C as describing the theory of symmetric monoidal categories, then the object of C would be something like formal tensor expressions, so something like this. And morphisms would be composite of structural morphisms, modulo axioms. Okay. But again, there is nothing which says that this is the case. So this is only a category. Yeah. Okay. And now we have this category. So actually, this is a groupoid because here we want these morphisms to be invertible. Okay, so it's going to be a groupoid. And we suppose fixed a subgroupoid. So with the same objects, but so we only take part of the morphism, and this subgroupoid specifies the part of the structure we are interested in strictifying. Again, if we have the symmetric monoidal categories example in mind, then alpha lambda n rho, the subgroupoid should be generated by alpha lambda n rho, but not gamma. So we don't want to strictify gamma because this is what we have. So in such a situation, one operation you can perform is quotient the category C by the subgroupoid gamma. So this means that we want to turn the elements of W to identities. Okay, so we take the quotient of C by W. Okay, so this is specified by a universal property that you can imagine. And so the question is, when does making such a strictification, so when does taking such a quotient does not change anything, and by does not change anything, we want that the quotient functor here is an equivalence of categories. Okay, so
just could you back up one slide? W is the isomorphisms. The group. No.
Yeah. So we have
everything is isomorphisms, but you want some of them should be strict.
Yes, exactly.
And so you take it to you're localizing what you want strict.
Yes, exactly. So I'm quotienting. So I'm not localizing. Localizing would be formally inverting, but here this is a groupoid. So we really want to quotient. So make it turn into identity.
Oh, but it's the same. I mean, for groupoids, it's okay. Fine, perfect. Okay, thank you.
So usually localizing, you would say in a category you want to formally make a morphism invertible, but here it wouldn't change.
Here everything is isomorphic anyway, so you don't gain anything. Okay, fine.
And so when we have this property, intuitively, this is the case when W does not contain any non-trivial information. So we can formalize this by the notion of rigid groupoid. So we say that the groupoid W is rigid when this one of these three equivalent conditions is satisfied. So one says that any two parallel morphisms are equal. So whenever you have two morphisms from X to Y, they are necessarily equal. So another way to say that is there are no non-trivial automorphism on any object. And the third way to say this is that W is equivalent to a coproduct of categories one. Okay, so somehow if you are used to homotopy type theory, this should be the notion of set. If you want, this says that W is a set as opposed to a real groupoid.
So one second. W is a congruence also. In other words, with composition, it has to preserve this equivalence relation has to preserve composition also.
So W is a subgroupoid, so it does compose.
So for sure, it's a congruence. Okay, and now you're making it such a strict thing that it's a bunch of sets. That the quotient relation is a bunch of sets.
Yeah, so there are no two ways of relating two elements which should be identified. So when you want to identify X and Y, so which says that when there is a morphism from X to Y, then there should be exactly one
This is the way homotopy type theorists talk. Yeah. Okay, thank you.
So in homotopy type theory, you would say that something is a set when if two things are equal, they are uniquely equal.
Right.
Could you go back a slide? I'm sorry.
Yeah.
Previous one. So, okay. So yeah, for localization, the universal property would be that it sends all the morphisms in W to isomorphism. So here you're asking it sends all those morphisms to identities.
Yeah, exactly.
Interesting. And you could take a category, localize it, and then do the strictification also.
Yeah.
Right. Interesting. Okay, thank you.
Yeah, but here again, I'm only considering groupoids because this is the situation I'm interested in. So localization is really useless here.
Right.
So whenever you have a rigid,
it's not useless. Quotients are localizations in this case.
No, they are not equivalent. My point is that when you quotient, when W is rigid, then quotient and localization this is the same. But I can show you a very simple example where localization and quotient are not the same.
Okay, good. Even when all of W's are isomorphisms?
Yeah, maybe I can.
No, don't. That's
I can. But this. So I can explain you why. So for instance, so here in this is my category, and in red this is W. Okay, so this is a very easy category. So you see that if I am quotienting by G only, then I get this category, and these two categories are equivalent. Okay, so here everything is invertible, but I don't want to write it. But if I quotient by F and G, so now the subgroupoid is not rigid, then I get this category, which is obviously not equivalent to this one. So, and localization would not change anything. Okay, so localization, these are groupoids. Okay, everything is invertible. But you see that when you quotient, here you destroy some information, some hole in here, and these two categories are not equivalent.
Right. So on the left you have a collapsible groupoid, and on the right, okay, fine.
Yeah, this is rigid. This is not rigid. So this is my point.
Yes, thank you.
So whenever W is rigid, then the quotient has a very simple description. So the objects are the equivalent class. So you say that X should be identified to Y when there is an invertible morphism between them in W. And the morphisms are equivalent class of morphism, which says that F is equivalent to G whenever there is a pair of morphism in W, so making this diagram commute. And how do you compose morphisms when you have F from X to Y and G from Y to Z? So here you know that the equivalence classes are the same, but they are not necessarily from the same morphism exactly. But since you are in a rigid groupoid, you know that they are in the same equivalence class. So this means that there exists exactly one morphism in between them. And so you can take this as a composite. So when W is not rigid, then this choice of mediating morphism here might not be unique. And whenever you make the quotient, you might want to identify this. You would want to identify these two compositions. So this says that this suggests that whenever we want to quotient, we should first rigidify the groupoid and then go back to previous case. Okay. So you can say that the rigidification of W in C is the category which universally identify any two parallel morphisms in W. So you make W rigid in C, and there is a simple proposition which says that the quotient can be obtained in two steps. So first you rigidify and then you quotient, but the point is that the quotient admits the very simple description I gave earlier. And in particular, this means that the canonical functor, because of this, the canonical functor from C to its quotient is always surjective on objects and full. Okay.
Did you tell us how to rigidification?
No, but this is a purely formal thing. So you just identify two morphisms which are parallel, and then you take the congruence generated by this, and you quotient morphism by the congruence generated by this.
So it's another quotient category?
Yeah, but so this is a different kind of quotient. So here we are identifying morphisms. We are not touching to the objects. Whereas the traditional quotient, this quotient here, it does identify objects and remove morphisms also. So this part here, it's only identify morphisms, and this part here, it makes some morphisms identities. So it's this different kind of quotient.
Thank you.
And what you can show is that this quotient functor is an equivalence of categories if and only if W is rigid. So because of this, you only have to show that this quotient functor is faithful if and only if W is rigid, and you can have. Okay, so now we can try to have a coherence theorem for this thing. So again, we are a very abstract situation, but still I claim that it is interesting. So we say that an algebra for C in category D, this is just a functor, okay? So you think of the objects of C as describing the structure, and this functor, it does interpret the structure into some semantic category, okay? So maybe you want to take D to be set or cat. Okay, and we write, this is the algebra for the category of algebra of C and D, but this is really the functors and natural transformation. So what you can show here is that a functor from C to C prime is an equivalence if and only if it induces an equivalence on the algebras. Okay, so what you want to show here is here the situation you have in mind is whenever you have monoidal categories and strict monoidal categories, and so you want to show that these two, whenever these two structures are equivalent, these two structures are equivalent if and only if they give the same notion of monoidal category. Okay, and this is something you can show. Okay, so this is Yoneda yoga. Okay, maybe we don't want to read the proof here, but this is purely formal. And
I would call it Morita equivalent.
yes. So this one is not Morita equivalence. Okay, so this one is you just this is just Yoneda because you are looking at the semantics in all categories D's at once. Yeah, and you want to have an equivalence which is natural indeed. So Morita equivalence would be really this notion here, and which is what you expect. So you expect that these two structures, this functor here is an equivalence if and only if they have the same algebras in cat. Okay.
Okay. Only in the special case do you call it Morita equivalent.
Yeah. And this is a conjecture, but really I don't know. And Morita equivalence is complicated. So what I know is that it cannot follow from purely formal theorems, because you know that this equivalence here is somehow identifies more than just equivalence of categories, because you know that this Morita equivalence is correspond to having the same Cauchy completions or So it means that you can have two categories here which are not equivalent, but which give rise to the same categories of algebras in CAT. This is Morita equivalence in CAT. So maybe this works for this question situation. I really don't know. So this is a conjecture, but it doesn't cost much to say conjecture. But really, I wouldn't know how to start proving it. So, okay. So next question is, how do we show rigidity in practice? Okay. So again, we are interested in the case where C is a composite. So what I said earlier, it would work whenever C is not a composite, but W has to be a composite. For this, we want to maybe use rewriting. So I'm going to use, since I'm in an abstract setting, I want to use abstract rewriting. So an abstract rewriting system, this is just a graph, okay? This is just another name for a graph. So it consists of two sets, P0, P1. So this is a set of vertices, so X, Y, Z. P1 is a set of edges, F, G, H. And S and T, they associate to every edge its source and target, okay? So this is an abstract rewriting system if you want. Right. So whenever you have an abstract rewriting system like this, it generates a groupoid with P1 tilde as a set of morphisms. Okay, so the morphisms in P1 tilde are just zigzags, if you want, in your graph. Okay, so you take paths, undirected paths in your graph. And also, of course, this is a bit more quotiented. So if you take F and F backwards, this is the same as doing nothing. Okay. So you generate a set of morphisms, and here you have also a source and target morphism. So this is a set of non-directed paths, if you want, and you have an extension of the source and target, as you expect. So now I want to take in account coherence. So I need to introduce more information. And I say that an extended abstract rewriting system, this is more information, and what I add as information is a set of two cells, okay? So this is a new set P2 with source and target maps, which go into the set of undirected paths, okay? So this means that you can figure the element in P2 as some kind of two cells whose source and target are zigzags or undirected paths in your graph, if you want, okay? And you have the globular identities that should be satisfied so that it really looks like this shape, okay? So
I think of term rewriting systems.
Sorry?
Should I think of term rewriting systems here?
Yes, but this is abstract writing system, so this is not a term. So in term writing system, this should be a term, okay? But here, this is just a point. A term has more structure. You have variables, you can substitute terms and so on. So you can think of term writing system, but you don't have really terms, okay? You just have points if you want. So you're rewriting points. So Y rewrites to Y.
Okay, thank you.
Yeah, and also when you start doing this kind of construction, so you might want to go on the right, and actually there is one way of going. This kind of structure has been studied under the name of computad or polygraph. Okay, but yeah, I am going only to stay at the very low dimensions.
Samuel, can you just say one more time what the difference between P1 and P1 tilde is?
So P1 is a set of edges,
right?
And P1 tilde is undirected path generated by edges.
Okay, thank you. Oh, so the map is an inclusion?
Yes, this map is just the canonical inclusion of an edge as a path of length 1.
Okay, fine.
So again, the situation we have in mind here is that P0 should be abstractly think of formal expressions. P1 should be generated by structural morphisms, and P2 should be the coherences we want to have. Okay. So whenever you have
so that's why you don't talk about P2 tilde, because you don't have you don't want to talk about composition of coherent of okay, fine.
Yes. So you would do this if you want to think how I use maybe my basic coherence axioms in order to fill in some big diagrams, for instance. This is the P2 tilde. This is what you would like to.
Yeah, but then you would need something like P3.
Well, I assume that here it's because your coherences, the relations between the coherences are exact, not up to a higher order coherence. It's a simpler situation.
Yes. Exactly. So in fact, if you take these things and you go if you take the most general notions, you go on you don't stop at any particular dimension. So you get a notion of polygraphs, okay, and you can show that these polygraphs they describe somehow three omega categories, and there is even a model structure on omega cat in which the cofibrant objects are those polygraphs, okay, and somehow filling in constructing such a polygraph and trying to fill in all the disk higher dimensional or sphere, sorry, by disk. It corresponds to taking a cofibrant replacement or constructing a resolution. Okay, so this is an intuition which is valid and which can be made very precise. Okay, so whenever you have an extended abstract rating system, it does present a groupoid, which is the groupoid generated by P0 and P1, and you quotient the morphisms by the congruence generated by P2, as you would expect. And you say that two extended abstract rating systems are Tits equivalent, okay, so, whenever they present the same groupoid, okay. So there are many ways of describing a particular groupoid. And this is the notion of these are somehow presentation and this equivalence says that they present the same objects. There are two descriptions of the same objects. And this name, it comes from a group theory where you can think of this as some form of presentation of a group if you want, and this equivalence which says that two presentation of groups present the same. So one question which is interesting is how can we characterize this equivalence, or at least how can we modify a presentation in order to while keeping the same presented category. So there are two following Tits transformations. Actually, it's even possible to give a complete set of transformations, but I don't want to do this today. So suppose that you have an extended abstract rating system like this with a two cell of this form, okay? So A, it goes from fg to f prime g prime. Then you can think of two transformations on your extended abstract rating system or polygraph. So once there is one transformation which says that if you are in a situation where you have this cell A, and it happens that this cell A can be derived from some other two cells, okay? So maybe there is this cell here, but if you look at this diagram, then maybe you can fill it in with smaller coherent cell and have this coherent diagram filled in without A. Then you can remove it, and if you remove it, you won't change the presented groupoid. So this is one T transformation. And another one is the following one. So suppose that F is just a generator or an edge, so it belongs to P1 as opposed to P1 tilde. And here on the rest of the boundary, F does not occur. Okay, so somehow this cell here, it says that F, since everything is invertible, it says that F should be considered as equal as the rest of the boundary. Okay, and in fact, if you take this extended abstract rating system and you can then remove A and remove F. Okay, and if F occurs somewhere, then you can just replace F by F prime G prime G minus 1, the inverse of G. And it won't change again the presented groupoid. Okay, so this is just to say that there are this kind of transformation, and this is sometimes useful whenever you have a polygraph which has good properties. But you are interested in other polygraphs, then maybe you can take your polygraph with good properties and transform it into your other polygraph. And since you know that you keep the presented groupoids, then everything is going to be fine. Okay. So suppose that you are given an extended abstract rating system together with a set of edges which you call W. Okay. So again, we are in a situation as before, but the same situation as before, but now you have more information because P1 is directed, okay? So there is some kind of direction in P1, even though you consider the groupoid generates. And of course, we are interested in making W strict. So we say that P is W convergent when it is W terminating. So this means that there is no infinite sequence of morphisms in W. Okay. So if you use the morphisms F0 in W, F1 in W, and so on, at some point you will have to stop on an object which is not the source of any other morphism in W, and which you would like to call a normal form. Okay? And there is another property which you want to show, which is local confluence. And this local confluence property, it says that if X can be rewritten thanks to morphism in W to Y1 and to Y2, then there exists a pair of morphism in W. So the star here means these are paths, okay? But here they are just edges. And such that they are related by the congruence generated by P2. Okay, so these are the usual conditions from rewriting if you are used to this, but specialized to W. And whenever you want to have a commutation of diagram, you want to have a commutation up to the morphism in P.
The logicians call this Church-Rosser condition.
Yeah, exactly. So this, yeah. The Church-Rosser property is slightly different. I will mention this just after that, but this is very related to this.
Can we just back up for a second? Not the slides. It's just this. Given two presentations, you can't compute whether or not they're isomorphic groups. It's not computable, I think. General groups.
Yeah, I expect that this is not decidable. Yes.
Right, not decidable. And you're aiming for something decidable or something like that, or you just.
So I'm not taking two random presentations and trying to know whether they are equivalent or not. So this is not what I'm going to do. What I'm going to do is that I take one presentation which doesn't have good properties. So then I transform it into another presentation by T transformation, which has good properties. And then since I use T transformation, I know that these are talking about the same thing. Okay. So
okay. Fine, that makes sense. Thank you.
And also because of this property here, you know that if you take any element and you start rewriting in W starting from X, so then you know that you will have a path of or a morphism which is composed of transition in W, and you will end up in some normal form, some object which is not the source of any other morphism in W, which is called a normal form. Okay, so there is a particular path NX from its normal form. Okay, and then you have standard rewriting techniques. So this is as usual maybe, but adapted to this more categorical setting, but really no real new content. So there is this Neumann lemma, which says that if W is P is W convergent, so it has these two previous properties, then it's W confluent. And W confluent, it is almost the same as before. So if you have two paths in W, then you can close them in W in such a way that these two morphisms are related by the congruence generated by P2. But here, compared to before, these are two paths, okay? Instead, directed paths. Instead, as before, as two transitions. Okay? And the idea is you can pave this with the local confluence diagrams. And then there is this Church-Rosser property, which is the following one. It says that if P is W convergent, then two parallel W morphisms in the presented groupoid are equal. Okay? And this is really this is also this is quite standard. Okay, basically you just have to use so you have a canonical path from X to its normal form. Okay, and so suppose that you have a morphism. Maybe I should say that. So suppose that you have a W morphism. So this W morphism, it is a zigzag, if you want. It is an undirected path, so it corresponds to a zigzag of directed paths, a zigzag of morphisms. Okay, so this one is inverted, this one is taking forward, this one is inverted, taking forward, and so on. Okay, so you can decompose it in this way. For each of these objects, you can rewrite to a normal form. Okay, But since you are confluent, you know that all these normal forms, they have to be equal, okay, because of confluence. And so you know that this whole path here is actually equal to normalizing to x and then taking the normalization to y backwards, okay? And so this path here, this morphism here, it is equal to this canonical composite, which only depends on x and y. And so when you take two morphisms which have the same source and target, they have to be equal because they are equal to this canonical morphism. Okay. And so another way to say this is that if P is W convergent, then the groupoid generated by W in P is rigid. Okay? So this is a concrete way of checking that groupoid is rigid. Okay. And last thing is that you can take n of P to be the subcategory whose objects are in normal form. So normal forms, if you think of monoidal categories, maybe I'm saying, yeah, maybe the normal forms. So you want to have this direction which says that you tend to associate things on the right, okay? So this is your direction, and normal form would be expressions which are fully bracketed on the right. And so whenever you are in such a situation, you can show that the quotient is equivalent to the subcategory, the full subcategory on normal forms, okay? And this would correspond abstractly, if you want, to strict monoidal categories, okay? Because in strict monoidal categories, the tensor is strictly associative, but one way of saying this also is saying that this fully associative tensor is represented by a tensor expression bracketed on the right. Okay, so maybe I want to skip this. Okay, so somehow we have shown that this the following definition of coherence of P with respect whenever we have a polygraph P and a subset of generators W or morphism W which we want to make strict, we have shown that the following definition of coherence are equivalent. So every parallel zigzags which edges in W are equal, which means that the subgroupoid generated by W is rigid. The quotient map is an equivalence of categories. The inclusion of algebras is an equivalence of categories, and the canonical inclusion from normal forms into P is an equivalence of categories. Okay, so somehow we have all the abstractly all the coherent theorem. Okay. So then what I want to show next, okay, so I don't know how far I will go. I just promise that I will stop soon. I think I have too many slides, but I won't show them all. So I want to explain how to do this for term writing system. So in order to reason about actual categorical structures, okay, so the previous setting was fine, but you cannot really show, for instance, the coherence theorem for monoidal categories, at least not directly. So in order to do this, we should go from abstract writing systems to term writing systems.
Well, why does it fail? Why can't you? It looks like you should be able to.
No, because a functor from C to your category, it does not preserve products, or it does not preserve tensor. You have no structure on your objects. So your objects are just points. So you can't say I want to so you want your how would you express your tensor? The fact that you should have a tensor in your algebras or something like this. You cannot. These are just points if you want.
Okay.
So somehow you should be able to say that you want a tensor in your algebra, and the tensor is binary, and the unit in this null array, and so on. And this you have no way to express this. So really, in order to express this, you should go to term writing system. So a term writing system P consists of the set P1 of operations with arity and the set P2 of equation between the generated terms, okay? So for instance, the term writing system for monoids, it says that we have as operation M, which is a multiplication which is binary, and E, which is a null array operation. And the equation should say that multiplication is associative and E is a unit on the left and on the right for multiplication. So again, compared to the previous setting, here you have formal expressions, whereas before you could just say we have equation between points, which is not really interesting. Okay. And then if you want to add coherence, then you should consider extended rewriting system. So again, you want to add another layer. And what you say is that you add equation between paths formed by the two generators. So here you orient them and you add the equation between those paths. Okay. And maybe the important point is that, so here M is not this M, so M is a natural number. So if you fix two natural numbers, then if you consider the home between M and N, so the home, it doesn't make sense in here. I have to explain how to make a Lovier theory first. So, sorry. So I just want, I should say that. So a Lovier theory, you should know that it is a Cartesian theory, the category such that the objects are integers and the Cartesian product is given by addition. Okay? And here, it is well known that a term rewriting system would present a Lovier theory, and it's natural to say that an extended rewriting system should present somehow a two-Lovier theory. And what is a two-Lovier theory? It is a Cartesian two category with invertible two cells. So it is enriched in groupoids if you want, such that the same condition is satisfied. So any two term rewriting systems or extended rewriting system, it induces a two Lovier theory whose morphism from M, so the objects are natural numbers, and the morphism from M to N are N tuples of terms with M variables. And the two cells are generated by the two generators, and then you quotient by the relation. Okay. And we say that an algebra for a two Lovier theory is a product preserving functor from T to cat. And then if you take the Lovier theory presented by Mon, the previous Mon, this is a monoidal category. Okay. And what I wanted to say here is that if you restrict to terms from M to N here, so from a fixed arity, so you restrict from terms with a fixed arity, and you take n tuples of terms, then you get an abstract rewriting system. So there is somehow a home for those term rewriting system, which is an abstract rewriting system. And this is how we can reuse all the previous properties. Okay.
And you're only talking about a single sorted Lovier theories here. Like you care about the multi-sorted case?
Yes, I wrote P1. I started things at 1 and not as 0 because you could add P0, but it wouldn't change anything, or it would not be more complicated. Or
okay.
But so this is just for simplicity here. We could handle multi-sorted cases.
Okay, cool.
Okay, so this is how you can describe algebraic theories with two Lovier theories, and I don't claim any originality here, or at least in this setting. Maybe the originality is more in the use of rewriting to handle this kind of situation. But this point of view was taken already by Nathan Janowski, for instance. So I guess this is part of the reason why I got invited in here.
No, you got invited because you wrote a nice paper, and I was trying to understand it.
Okay, so let me detail a bit. An algebra for this Mon, it consists of a functor from the presented Lovier theory to cat. So it consists of a category, which is the image of one, and you only need to have the image of one to have the image of any object because it has to preserve Cartesian products. So the image of n should be C to the n. So this is the Cartesian product of n copies of C. And here, this is of arity 2. So the interpretation or the image of M, it would be a functor from C2 to C. The interpretation of E, the image of E, it should be a functor from 1 to C. okay? And then you get, because of this, you get natural transformations which correspond to the one you expect in monoidal categories, and because of this, you get the axioms of monoidal category. Okay. So now you want, and this is really the situation you want to address. So you want to fix a two-term writing system with a subset of the two generators, which you are interested in quotienting out. Okay, so I write W's for the 2-1 categories it generates. And you say that W is too rigid when any two parallel two cells are equal. And you can show what you can show. So this is really applying the previous theorem on home sets. Okay, so this is really previous theorem. There is no new content. You can show that the two functor here, the quotient two functor, is a local equivalence if and only if W is too rigid. Okay, and the local equivalence, it means that this two functor, it induces a functor between home categories, and for any two objects, this functor induced between home categories is an equivalence. Okay, and you can show that if P is W convergent, then W is too rigid. Okay, so this is really a previous theorem applied home-wise. And so before we wanted to check how. So this local confluence diagram, but now you can check this local confluence diagram. It is well known from writing theory. You only have to check what is called critical branching. So critical branching is a minimal non-trivial overlapping of the left member of two generators. And the one theorem says that if P contains a tree generator corresponding to the confluence of each critical branching, okay, so the sentence should be finished. Then it is coherent by which we mean that so here it's a critical branching. You want to consider only critical branching with respect to morphisms in W, and when this is the case, then you are too rigid. Okay, so again, this is some form of coherence property. Okay, so for instance, let me explain how this applies, and then maybe I will stop there. So consider the term writing systems for monoids. So here we want to take W to be all two cells, okay, because we want to quotient with respect to alpha, lambda, n. Okay, so first thing we can observe is that it is terminating, okay? So how do we show this? Well, for these two rules, you see that they tend to decrease the size of terms, okay? Here you have the terms with two operations, and here you only have a variable, okay? So this is easy. And this one, they tend to put things on the right, okay? So there are ways to formalize this, but intuitively you can have this intuition. So the critical branchings are ways to overlap the left members of these rules, okay? So for instance, if you take, I don't know, for instance, these two rules, lambda and rho, then these are the left members. And here you say that this term here is an overlapping of this non-trivial and minimal overlapping of these two left members. What does it say? It means that here you have this rule which says that when you multiply by E on the left, then you can just go to X. So here this rule does apply, okay, because we are multiplied by E on the left. But when X is E, then you can also apply this rule which says that when you multiply by E on the right, then you can just rewrite to X. Okay. So this is very combinatorial, and you can have a computer do this, okay? So you can compute all the overlaps, and here in this case, you see that there are 5 overlaps. The next thing you can show is that all these critical branchings are confluent, okay? So using these rules, there is a way to close the overlap. So for instance, here, this is the overlap I was speaking about, so this is very easy. But for instance, here, with this rule here, you can apply alpha associativity, you can apply in the inner term or in the outer term. And so you can use this rule either to change this term to this or to this. And in this situation, you can show that by chance, you can close it in this way. Okay, and so here you can observe or check that all the 5 critical branching are confluent, and these are confluent there. So this suggests that we should put these 5 axioms as coherence relation, okay? So now we want to consider the extended term writing system with these 5 axioms as these 5 yes, coherence relations. And because we have convergence, so this is terminating, okay? And because we have added all these coherence relations, this is also W confluent, and so this is W convergent. And we have shown that when it is W convergent, it is too rigid, okay? So this means that because of this, any diagram made of parallel two cells is going to be any two morphisms are with the same source and the same target are going to be equal modulo these axioms. Okay, so this is the property we wanted to have. Okay, the only annoying thing is that we have 5 axioms here, whereas for monoidal categories we only have 2 axioms. But in fact, we can get back to 2 axioms by using these state transformations. Okay, so I did not explain what they were for term writing system, but they're very similar to what they were for abstract writing systems. And so we know that for in this case, all the morphisms, all the parallel morphisms in W are equal, so we are rigid. This is going to stay the same because it does present the same category with only these 2 axioms, because we can show that some of these, so B, D, and E are superfluous, and I can remove them by T transformation. And so we can deduce that any structural morphisms in a monoidal category are equal. Okay. And maybe I should stop here. So what I want to say maybe is that so the situation, when you study the situation, so for monoidal categories, it's not that interesting in the sense that it has been studied by almost everybody. Well, this is not very new. But for symmetric monoidal categories, you can adapt these ideas, okay? And why is the situation different? So first, the situation is different because you take W to be alpha, lambda, and rho. And also the situation is different because somehow this is not terminating, okay? Because we can understand the fact we have a problem here because here we are commutative, so x1 times x2, it rewrites to x2 times x1, which itself rewrites to x1 times x2, okay? So somehow we have this braiding or this symmetry we can apply indefinitely. And in order to apply our previous techniques, we should try to refine the way we write things and take in account maybe this numbering of variables. So maybe this one is fine, or maybe, yeah, this one is fine because it puts variable in decreasing order, but this one is not fine because it puts them in decreasing orders. And anyway, you know that this one is superfluous by this transformation because this one should be equal to this one because of G. Okay, so then you can work out the details and you can show the coherence theorem for symmetric monoidal categories. And I just want to say a last thing, which is that I wanted to the first thing I wanted to study was this case of ring categories. So this categorification of rings. And here you have these 2 structural morphisms, and you can make one an identity, but not 2. Okay. And I was hoping to use this setting to show this. So actually, I am still hoping to be able to handle this case, but there are many computations involved, and so it does take time. And I will stop here and take your questions if you have.
Mm-hmm. First, thank you. That was very nice. Let's thank the speaker. Any questions?
Yeah. So this was great talk. Thank you. I'm curious. So this can handle like monoidal categories, symmetric monoidal categories. Can you do things like double categories?
No, I don't think so. Or not easily. I have to think about it, but I don't think that the double categories that do fit at least directly in this setting.
Right. Yeah, I guess it wouldn't you wouldn't need to even make sense of that.
Yeah, but
Okay.
I don't think that in algebra. The question you should ask, we should ask ourselves is it an algebra for a Liouville theory? And
Well, it's not essentially algebraic. I mean, it is essentially algebraic.
it could
It's
be
not
essentially.
algebraic, but it's essentially algebraic. It's two sorted.
So yes, but okay. So maybe I have to say I didn't think at all about this. So maybe I'm thinking wrong. So but here categories also are essentially algebraic, and it's not a problem. Okay, here because we are taking algebras in CAT. Okay, so one thing we could do is take maybe algebras of a Liouville theory in double categories or something like this. But
Yeah,
yeah.
because I was thinking like normally in double categories you have one composition that's only weakly associative. So I was thinking like, oh, you could strictify that
So you want double by categories?
double bicategories.
Oh.
I don't know. Maybe I'm using the wrong terminology.
Usually, bicategories are the compositions are both strict. I mean, they're category objects in the category of categories. You're looking at bicategories in the category of categories.
I don't know. All I know is that the definitions I've seen were double categories. You have like vertical composition is strict and horizontal is non-strict. So that's what I was thinking. But yeah. Anyway,
by default they are both strict, but yeah, I guess you can come up with all these kind of variants.
Yeah.
But certainly this does not fit. I can't use something from the hat and say I can handle this immediately.
Right. Right. Very cool. Thank you.
Larry.
Okay. Yeah. Hi. Thanks for a really nice talk. So my question concerns a few of the remarks that you made in the talk that had to do with computer support for the kind of work that you're doing.
Mhm.
So at various places you said, well, you could check this on the computer. You know, we were looking at the local confluence of the set of rules and stuff. So I have some experience using computer tools to check the confluence and termination of rewriting systems. And I'm wondering whether all of the things you do really could be done on the computer, or if what you're doing kind of goes beyond what you would use to in that kind of work. Like, for example, you had at the very end, you were doing rewriting modulo equations, right, for the symmetry equation and various other kind of stuff. So I'm wondering if what you're doing goes beyond what people usually do, or if you could actually use off-the-shelf computer tools to check the coherence theorems the way you formulate them.
So what can I say? So I have developed my own library to do rewriting. So
Okay, yeah.
So in this way I can avoid trying to check whether it does fit with off-the-shelf solution. But but actually, so I did some experiments and some computation. But to be honest, most of the computation I did in this work, I did them by hand because precisely it's not exactly traditional rewriting we want, or we need some kind of variants of traditional rewriting. And actually, for the symmetries, I'm not doing rewriting modulo, but I am actually what we want is not to precisely, we don't want to work modulo commutativity, but we actually want to really take seriously the order of variables into account. But this means that it breaks substitution because it's not stable under substitution, and then you have to be very careful and so to be honest, this could be done on a computer. I'm sure. So I'm not lying or overselling things, but I don't think this is implemented anywhere as I would like to right now.
Okay, thanks very much.
Okay, any more questions? Anyway, Samuel, thank you very much. It was a pleasure. It looked like an interesting paper, and now I think I might even be able to read it. One second.
Thank you for having me.
Somebody wrote something in the chat. You have any computer formalization, question mark? I believe an inductive computational proof of semi-associativity coherence has been posted on a Coq Club mailing list a long time ago.
Yeah, so no, I don't have any computer formalization. So from my experience, it's better to have paper formalization or full paper formalization before trying to dive into computer formalization. And for now, I'm not entirely satisfied about the state of affairs. So for abstract writing systems, this is fine. The first part. For term writing systems, there are still things which should be improved or which should be understood better. And I want to do that before being able to formalize. So in particular, I was hoping at some point to use some of the theorems you developed for this Lovier-2 theories, but it turns out that it didn't work for very subtle reasons. So I was very disappointed because I was hoping that I could just use this theorem, but it turns out that it wasn't the case.
Okay, thank you very much. It's a pleasure. Thank you. It was a very interesting talk, very informative. So that's the end of the season. We'll see you all in September, I hope, and we're looking forward. We have some nice talks planned, and if you want to give a talk, let me know. Send me an email. Okay, thank you, Samuel. Stay in touch, and we'll have you back again. It's a very interesting project.
Thank you.
Thank you very much. Take care.
Bye.
Take care, everybody.